Okay, so thank you very much. I'm here to present the development of my doctoral thesis that is called, entitled Model Predictive Control Applied to Turbulent Flows, and supervised by Professor Stefano Discetti and Andrea Melambila. So basically, as it's already clear from the title, actually I'm trying to apply a specific control technique to fluid flows, while controlling flows means basically manipulating them in order to optimize a specific target. Let's start from a more practical point of view. There is an example here. So there is an airfoil. There is a condition of high angle of attack. This could be seen as an airfoil of an aircraft during an approach to the airport phase. And if we put, this was a result from Puri encoders, if we put specific jets in specific position over the airfoil, we can just delay the separation and increase the efficiency of this delicate phase of the flight. Of course, all the application of fluid flow control, there are many objectives, of course, and they're appealing for also other industrial sectors. So just imagine how the drag reduction has received increasing attention for the automotive sector for reducing the pollutant dispersion. And among the strategies that we can use in fluid flow control, the active flow control is the one that is the most promising. It's characterized by three main items. First, there are the sensors. They are the ones that are telling us information about the state of the flow, the state of the system we want to control. Then you have the actuators. They are the devices that are actually controlling the flow. And then there is the control strategy, that is the algorithm that is telling us how to select the actuator response. One of the strategies that is receiving great attention in controlling the flows is actually the model predictive control. To understand its working principle, I really like performing the comparison with the game of chess. So there is when we play chess, we try to predict as much as possible the steps of the game into the future. Of course, we need a model in this case. We need a model of how our opponent will reply to our actions on the chessboard. And of course, I'm saying as much as possible because we don't have a model that is perfect to have prediction till the end of the game. So we focus only on the first 3-4 steps. And of course, the action we do, it's only one on the chessboard, and it's a result of interaction between optimization based on predictions. And just imagine that these predicting capabilities are widespread also in nature. There is the dragonfly that actually is using predictive control to capture their prey. There is, sorry, there was an insect here. And when it comes into applying this control strategy for fluid flows, we generally have a reference. And we want the system state here at J in order to follow this specific reference, and we need to select this input here. And in the selection of this input, we generally have information from sensors that are closing the loop. So this is a closed loop control strategy. And what happens inside the model optimizer is to start from a measurement of the system state. We use the model we have of the fluid flows to make prediction inside a prediction window whose length is finite because the predictive capabilities of the model are limited. And we have control action because the model is accounting also exogenous input. So what we do is to define a reference. In this case, it's the green line here. It's basically the sign of a cost function. And we optimize this cost function that is based on the prediction by performing an optimization over the optimal control strategy. After we solve the optimization, that is we can consider also like constraints on the input and on the output. We only select the first step and we repeat the process. Of course, we need a model of the flow. There is already a model. There are the Navier-Stokes equation, but just considering solving numerically them on the fly. So this is computationally expensive, and it's making the control impossible to be applied for time reasons. Of course, we need then a model of the fluid flows, but this is really complex to obtain since of some of the properties of the flows. Actually, these are multidimensional. There are time delays in sensing and actuating, and they are characterized by multi-scales and multidimensionalities. So we need model order reduction techniques, and this is where my thesis is more or less focused, so in the application of model predictive control and solving all the problems related to it. And in having this model, we need to perform a trade-off between the accuracy and the computational cost. This is a timeline of all the activities I did so far during the PhD. So first year was mainly focused on literature review, basically model predictive control, general control theory, and nonlinear system identification to obtain this model or these reduced models. And some problems like hyperparameter selection in control and robustness to noise and model uncertainties, because the model always will have uncertainties. And well, I started applying model predictive control to a first laminar 2D problem. That is the fluid pinball. I'm going to talk about it in a moment. And this arrived to a first publication at the beginning of this year in the Journal of Fluid Mechanics. The title is Self-Tuning Model Predictive Control Applied for Wake Flows. And this is the fluid pinball, the problem I was telling you about. It's a problem, fluid dynamic problem, 2D laminar chaotic, but with a simple dynamics. Actually, we selected it because it has a really wide actuation space. And basically, there are 3 cylinders put at the vertices of a triangle. We can select independently the rotation of the 3 cylinders here, and this will be our control action. In this publication, what we did was to perform first the nonlinear system identification, because we need the model. And this was done by selecting the coordinates. For our case, since it is a separated flow, selecting the coordinate was pretty easy. So we selected the forces and their time delayed version. In this case was, they were the CD, the drag and lift coefficients, and the derivative in time. And we applied a technique that is called SINDI, sparse identification of nonlinear dynamics, to discover the dynamics of these forces as a function of themselves and also the actuation parameters. And basically, this SINDI model, it's a method that gives us ordinary differential equation telling us the dynamics of these forces by performing a sparse regression in a library of function that is selected by the user. When it came into applying the model predictive control with this model for the fluid pinball, we discovered that actually we needed to select in the design of the cost function, that is the cost function telling us how far we are from the reference, we needed to select some hyperparameters, and we did it externally with an offline optimization using Bayesian optimization. And because if you select these parameters by hand, like the length of the prediction window, the frequency of the control, and some parameters balancing all the objective you have in the cost function over there in the optimization, you generally, if you select them by hand, you generally fall in a local optimal solution. And we also were focusing on noise, robustness to noise, since we wanted to apply these in experiments. And actually, these are some results. It's an animation. We have the drag coefficient, lift coefficient, and the actuation selected. If we select the parameters by hand, actually, we end up in a local optimal solution. The target here is to reduce the drag as much as possible and to stabilize the lift around the 0 value. And it's pretty clear that if we do it by selecting the parameters using Bayesian optimization, the performance is pretty higher than the first case. And in this case, we were, instead of setting the lift around 0, we were making it follow a sinusoidal trajectory. And model predictive control was pretty capable of doing that. Well, after that, we were targeting to apply and to validate this in an experimental facility. We have it actually in the water tunnel. It's the fluid pinball is here. There is a picture. And here there is some flow visualization in which actually you will see the results of this in the next PhD presentation, I hope. And basically, we recovered the actuation mechanisms that were typical also of the DNS simulation. So these are some flow visualization. After that, we continued with another activity that was mainly based on understanding and creating the model to be embedded in model predictive control. And the first activity was still on the fluid pinball with control in this case, and the activity was about manifold learning. So we wanted to create this low-dimensional representation of the flows. And we did it with a technique that is called isomap. There is an archive here. The paper is under review from Journal of Fluid Mechanics. So what we do here is to maintaining the properties that there exists a manifold where the data relies. We use this technique in order to compress all the information we need of the flows to a low-dimensional representation. And then, so we do a mapping to a low-dimensional space. And then, since we wanted to apply to control, we pass from the dimensional space with another mapping to the physical space again. So this is a kind of encoding and decoding strategy. I'm not going to enter into the details of these, but if you have many questions, I will be happy to reply to them. And For future activities, I think I will mainly do a research stay in Paris, and will be hosted by Professor Onofrio Semeraro in Paris, and where we will mainly work on the trying to embed the capabilities of model-based approach, like model predictive control is, and model-free, like reinforcement learning, in order to have a general control framework that is applicable for more complex cases, like turbulent flows. So far, we only selected laminar flow. And if the time allows, also to try an experimental validation over a lab scale problem. This is a list of all the activities I've done so far, papers and contribution and conferences. And this was a list of the activity I was planning to do at the beginning of the PhD. So we're in the second year here. So the main topic now is trying to validate experimentally the contour approach of the first paper. So that's it from my side, and I will be very glad to reply to some questions.